So we've had a look at applications of Kepler's laws of motion in terms of estimating masses for different objects, particularly the planetary system, and estimation of masses of stars. Now, suppose we want to estimate masses of aggregates of many stars or even galaxies, then what do we do? Okay. Now, we have discussed determination of masses in two-body systems. If you have three-body systems of analytic solutions in very restrictive cases, and n-body systems is very difficult to get analytic solutions. And for groups of hundreds of stars or galaxies, the way we estimate mass is by resorting to what is called a virial theorem. Okay, and I will just state it over here. And for the MSc classes, I will derive it later. And basically what it tells you is that the kinetic energy of a gravitationally bound system in equilibrium is equal to -half of the potential energy of the system. Okay. And you know that the total energy of the system is kinetic energy plus potential energy. So if you plug that in, you'll get total energy is equal to half the potential energy of the system. So kinetic energy you can estimate from the motions of the stars or galaxies that make up the system. And the potential energy will then give you an estimate, which depends on the mass of the system, will give you an estimate of the mass of the system. Okay. Now, what are the assumptions that go into it? That the system is virialized. What does it mean? That it's in a steady state. Okay. Bodies could be in random motion, but there is no systematic outward or inward motion. Neither some explosion is happening nor collapsing, and no rotational or centrifugal force in the derivation. Okay. We can then use the virial theorem, these expressions, to try and estimate the masses of objects. So we'll just look at a couple of examples of that. And this is particularly useful in terms of galaxies as well as dense star clusters, such as the globular clusters. This one shows an image of the famous M87 galaxy, Messier 87 in the Virgo cluster of galaxies, where surrounding it, there are a lot of giant, many hundreds of globular clusters. Okay, there's some articles which I've sort of given a reference to over here, which would be interesting to read. Okay, now let's see how we go about it. Okay, this is a globular cluster, and we have discussed globular clusters earlier, but just for the sake of the MSc students who are new, that there are two kinds of star clusters. One are the open clusters and the other are the globular clusters. The open clusters largely reside in the disk of spiral galaxies, whereas the globular clusters form a halo around the galaxy. The open clusters take part in the regular motion or rotation of a spiral galaxy, whereas globular clusters, they move about randomly. Globular clusters also consist of stars which are metal poor. In astronomy, anything beyond hydrogen and helium are called metals, whereas the open clusters are rich in metals because it has formed from later in the evolution of the galaxy from material which has been enriched by the evolution of earlier generations of stars. So globular clusters in a way are more primitive systems, and they're very dense clusters, as you saw a short while ago in the two pictures which I showed you. Now, in a cluster such as this, the VR squared, which is velocities of the galaxies, would be roughly equal to the dispersion, the square of the dispersion in the radial velocities of these galaxies. There could be a systemic velocity as well, in the sense that the whole cluster could be moving. But while looking at the random velocities of the stars within a cluster or of galaxies within a cluster, we have to take out the systemic velocity out. For example, a whole cluster of galaxies may be expanding out due to the Hubble expansion of the universe. But on the other hand, within that cluster itself, the galaxies would be moving around in the potential of the cluster and have random motions. So similarly, in the case of a star cluster, the entire stellar cluster or the globular cluster will be moving. But in addition to the systemic motion, there would be random motions of the stars themselves. We can measure the radial motion from the velocity shifts, which are easy to do. In a very dense star cluster, doing proper motion studies are not easy. So we rely on the radial velocity measurements, but radial velocity just gives you only one component of the velocity. So if you look at the velocities of the stars in 3 dimensionals, here in spherical polar coordinates, it will be v theta, v phi, but v squared would be 3 times statistically average of the radial component velocities of the stars, which is 3 times the velocity dispersion of the stars in the cluster. Velocity dispersion or random motion of stars, where vi squared, this is the average velocity, one is divided by n to get the average velocity, which is v squared average, which is 3 times the radial component, 3 times the velocity dispersion. And then we just apply this relationship, which is kinetic energy is equal to minus half the potential energy. And I'll just show you 1 or 2 applications of it. I will not take too long over this presentation. So potential energy of a spherical distribution of mass m and radius r. Over here it is reasonably spherical, so this is not a bad approximation, but that may not always be the case. 3/5 gm squared upon r. Okay. Now potential energy I've just divided by n over here, so that it is per unit mass over here, unit star over here. One is again averaged, assuming that they're all similar, and then where m, the mass of the cluster, is equal to n stars into the mass of an individual star. In the case of a cluster of galaxies, it would be the mass of an individual galaxy. So this for, I've equated this, the kinetic energy, okay, twice the kinetic energy, so the 2 goes away, is equal to the potential energy, and that gives you m of the order of 5 r sigma r squared g. So I can measure sigma r from spectroscopic observations. So once I measure sigma r, then I can get the mass of the particular cluster. So this can also be done for clusters of galaxies, as we just mentioned. Again, we assume that the system is virialized, which is in equilibrium, and measurements we make of are representative of the system. And again, galaxies are moving about randomly, and we assume that most of the galaxies are similar, which is not strictly correct, but it still gives you a reasonable answer, at least to work with. It is from studies of the Coma cluster by Saikia in the 30s that he inferred the existence of dark matter. The Coma cluster of galaxies consists of over 1,000 galaxies, velocity dispersion of the order of 1,000 kilometers per second. And if you plug this in, you'll get the total mass of the order of 10 to the power of 15 solar masses. So this is the way that one can go about estimating the mass of a cluster of galaxies. Now, over here, the thing is that this galaxies will move about responding to the potential, not just of the galaxies, but all matter in it. So it responds to the dark matter as well. So it is because of that Saikia was able to infer that there is much more mass than can be inferred from the visible galaxies that we could see. Today, we have learned earlier when we talked about X-ray astronomy that clusters have a lot of thermal brennström gas, actually, which is much more massive than the galaxies put together. That is the intercluster medium, which gives out X-ray emission. But we know that the dark matter is what dominates. But in addition to the light that you see from the galaxies, there is also hot gas which emits in the X-ray region of the electromagnetic spectrum. I've just given you another example over here, 5 r sigma r squared g, the same equation we've applied to velocity dispersion in stars in the central region of one of the satellite galaxies of Andromeda galaxy, M32. This galaxy discovered by Gentile in 1749. It's at a distance of 770 kiloparsec. And from the velocity dispersion, one can estimate the mass to be of the order of 10 to the power of 7 solar masses in the central region of this galaxy. Other estimates give similar ballpark. It's about 1.5 into 5 into 10 to the power of 6 from a more detailed study of the rotation curve in the central region of the galaxy. So you can see rotation curves also basically employ Kepler's laws of motion, but one has to do much more detailed modeling because matter is not distributed in a point like a star. but it is more distributed in the form of a disk, for example, and one has to model the disk and look at how the velocity is going to change with distance from the center. So these are ways of actually determining masses using the virial theorem. I've just given you two examples. The other example which you mentioned, which one of you mentioned early in the beginning, was gravitational lensing. So I'll again very briefly touch upon that, for you to be aware of it. Some of you are already aware of it. Suppose we are observing a distant object from a distant object, and there is a galaxy along the path over here that, due to Einstein's general theory of relativity, space will be curved and the object will follow a curved trajectory. So when you project the source back onto the sky plane, one can form multiple images depending upon the mass and how it is distributed. If there was no lensing galaxy at all, what you would see is a single object over here. This shows how a light from a distant quasar bends around a warped fabric of space-time in the vicinity of a massive galaxy. So lensing can occur not only by the galaxy itself, but if the galaxy is in a cluster of galaxies, then lensing can take place due to the combined mass of both the galaxies as well as the dark matter which is present over there. So one can see that lensing is also a powerful tool for estimating masses of objects. This is just another view of a galaxy cluster, and you can see that these arcs are the ones where galaxies have been lensed. You can see that these arc-like structures over here are more distant galaxies which have been lensed by this cluster of galaxies. On the right, what you see is the artist concept on the right. Blue shading indicates location of dark matter. The scientists mathematically determine must exist to account for the nature and placement of the gravitationally lensed images. Okay. Now, just to write down the equations, that suppose you had a lens over here, and a source over here, and the observer over here, then the angle by which it would change, it appear to change, is given by 4gm r0, the line of closest approach, okay, divided by c squared. And even Newtonian calculations gave a factor of 2 over here, and Einstein's general theory of relativity gave a factor of 4. And as you know, Eddington's confirmation of this made Einstein very famous and provided one of the early proofs of the general theory of relativity. Now, using this geometry over here, one can write this down, given this is the angle theta over here, minus beta theta. I'm not done the derivation over here. You can again look this up in Carroll and Ostley, and ds is a distance to the source. Okay, ideally it would have been ds upon cosine, but the angles are so small it doesn't matter. And dl is a distance to the lens, and this is basically what is called a lens equation. And theta being is the angle over here, and because it's a quadratic equation, you'll get two solutions, theta 1 and theta 2, and beta is equal to theta 1 plus theta 2. One can show that as well. Now, this also, you can see that as long as you can measure theta and the distance to the source and the distance to the lens, you can go and get an estimate of the mass m. And this is the expression, m is equal to minus theta 1, theta 2, c squared upon 4g, ds dl, ds minus dl. Okay, now there's a negative sign over here, and that's just a convention because there are two solutions on either side. So one is given a negative number, and it's a matter of convention. It doesn't matter which side you put it. And so mass, you'll get a positive number for the mass. And once you know the distances and the angular separations, which you can estimate, you can get an estimate of the mass of the lensing object. Usually it is not a single object, usually it's a distribution of mass. And so for both the source as well as the lensing object, and one does very detailed modeling to try and find out how the mass might be distributed, and along with the estimate of the mass. Here again, I just reproduced this example on Carroll and Ostley just to illustrate that to you. This was the first gravitational lens which was discovered, 0957 plus 561, where you can see that there are two quasars over here, lensed by a foreground galaxy. This was discovered at Jodrell Bank Radio Observatory from a survey of radio sources. And you know that they're lensed images because they have absolutely identical optical spectra. So gravitational lensing is achromatic. That is, every part of the electromagnetic spectrum would be lensed similarly. And from the angular separations of θ1 and θ2, which is plugged into radians in this equation, and from the redshift of the object as well as that of the lensing galaxy, which were measured, they have calculated the mass of the object to be 8.1 into 10 to the power of 11 h inverse. This is just some scaling factor with the Hubble constant, which is related to the distances over here. And this is a good agreement. This is just a very rough estimate of it with more modern values from more detailed sort of modeling of the system. So you can see gravitational lensing provides another sort of important way of trying to determine masses. So here is our objects, what are called Einstein rings, where if an object is directly behind a lens, it can be formed, it can be seen to form a ring around it. These are images from the Hubble Space Telescope. There are also many other collages which you'll find in the web. And θe is referred to as the Einstein radius of this ring over here. These gravitational images are absolutely fantastic. So in terms of estimation of masses, I will just leave you with this stunning image of Abel 370, which is gravitationally lensed a lot of these background galaxies, which you can see as these beautiful arcs over here, right? And these are examples of what are called strong lensing. One can also look at weak lensing, where there is just a shear which you can determine from a large statistical sample of galaxies. But I think for our purposes, it is adequate to know that both applications of the virial theorem as well as lensing gives you estimates of masses of clusters of galaxies. And the virial theorem has other applications as well, including masses of stellar clusters, such as globular clusters, for example. Okay.